In mid-1943, in factories scattered across Germany, a machine was being produced that would forever change the face of armored warfare. It wasn't just another tank. It was a revolution on tracks. The Panzerkampfwagen 5, better known simply as the Panther, represented the pinnacle of German armored engineering during World War II. But how exactly did this machine come about? What technical challenges did it face? And why, despite its superiority in many aspects, did it fail to change the course of the war? This is the story of the incredible engineering behind the German Panther tank. If you enjoy this type of content about military history and engineering, don't forget to subscribe to the channel and leave a comment letting us know what time you're watching this video. To understand the Panther, we first need to go back to the summer of 1941. Operation Barbarossa, the German invasion of the Soviet Union, was in full swing. German panzer forces were advancing deep into Soviet territory, confident in their blitzkrieg tactics and the superiority of their armor. Panzer IIIs and Panzer IVs had dominated the battlefields of France and the Balkans. But on the Russian steppe, the Germans were about to encounter something completely unexpected. When the first Soviet T-34 tanks appeared on the battlefield, German commanders simply couldn't believe what they were seeing. Here was a tank that combined three critical elements that no other armored vehicle had managed to balance until then: thick sloped armor, exceptional mobility, and a powerful 76mm gun. German projectiles ricocheted off the T-34's sloped armor like stones thrown against a roof. The 37 and 50mm guns of the German panzers were practically useless against this new threat. The shock was immense. Reports from German officers on the Eastern Front described scenes of panic as T-34s simply drove through German lines, impervious to conventional anti-tank fire. One panzer commander wrote in his diary that it was like trying to stop an elephant with a hunting rifle. The Wehrmacht, which had conquered most of continental Europe with its armored warfare tactics, suddenly found itself technologically outmatched. In November 1941, a special commission was sent to the Eastern Front to examine captured T-34 tanks. Engineers, officers, and tank designers were impressed. The T-34 was not just good, it was brilliant in its simplicity and effectiveness. Its sloped armor not only offered protection equivalent to much thicker armor, but also significantly increased ricochet resistance. Its wide track distributed weight efficiently, allowing for superior mobility in muddy or snowy terrain. And its V2 diesel engine was reliable and had an impressive range. The German response needed to be swift and decisive. The German High Command summoned the two main tank manufacturers, Daimler-Benz and MAN, and Maschinenfabrik Augsburg-Nürnberg, to develop a new medium tank capable of confronting and overcoming the T-34. The specifications were clear. The new tank should have frontal armor capable of withstanding the T-34's 76mm gun, armament capable of penetrating Soviet armor at significant distances, and mobility at least equal to that of its Soviet adversary. What followed was one of the most intense design races in military history. Daimler-Benz, influenced by the T-34 design, proposed a tank that was almost a direct copy of the Soviet concept. It had a rear engine, a turret mounted in front of the hull, and even used the same sloped armor philosophy. It was a pragmatic design that could have been produced quickly. But there was a political and philosophical problem. The German leadership and many members of the High Command did not simply want to copy a Soviet design. They wanted something distinctly German, something that embodied the German philosophy of precision engineering. MAN's proposal was radically different. It retained the traditional German configuration with a rear engine and turret positioned in the center of the hull, but incorporated the sloped armor that made the T-34 so effective. MAN's design was more complex, more expensive, and more difficult to produce, but promised superior performance. In May 1942, after months of heated debate, MAN's proposal was selected. The Panther was born. Now comes the truly fascinating part of the story, turning the project into reality. The engineering of the Panther represents an extraordinary case study of technical ambition confronting practical realities. Each system of the tank incorporated significant innovations, but also monumental challenges. Let's start with the armor, the most visually distinctive aspect of the Panther. The frontal hull armor was 80mm thick, but it was angled at 55 degrees from the vertical. This angle was crucial. When a projectile hits an angled armor plate, it has to effectively penetrate a much greater thickness of metal. The 80 mm angled at 55 degrees offered protection equivalent to approximately 140 mm of vertical armor. Furthermore, the angle dramatically increased the chances of a projectile ricocheting without penetrating. But producing this angled armor was no simple task. The hardened steel plates needed to be cut with millimeter precision and welded at exact angles. The metallurgy behind these plates was extremely sophisticated. The steel needed to be hard enough to resist penetration, but not so brittle that it would shatter on impact. German engineers developed a specific steel alloy with nickel, chromium, and molybdenum that achieved the perfect balance between hardness and toughness. The Panther's turret was another marvel of engineering. Unlike the cast turrets used on many tanks, the Panther's turret was constructed with welded armor plates. The turret's frontal armor was 100 mm thick and also sloped, offering formidable protection. The turret's shape was carefully designed to minimize the vulnerable surface area. The sides were sloped inward, and the front had a faceted shape that increased the chances of ricochet. But the real genius lay in the armament. The Panther mounted the 75 mm KWK 42L70 cannon, and this was no ordinary 75 mm cannon. The L70 in the designation means that the barrel length was 70 times the caliber, or 5.25 meters of barrel length. This extraordinary length allowed the gunpowder to burn completely before the projectile left the barrel, resulting in extremely high muzzle velocities. The KWK-42's standard armor-piercing projectile left the barrel at a speed of approximately 935 meters per second. To put that into perspective, that's almost 3 times the speed of sound. At that speed, the projectile could penetrate 140 millimeters of vertical armor at a distance of 1,000 meters. This meant that the Panther could destroy virtually any Allied tank of the time at distances where it itself was almost invulnerable to enemy fire. The accuracy of this cannon was legendary. Panther commanders reported consistent hits at ranges exceeding 2,000 meters. This long-range engagement capability completely transformed tank combat tactics. A well-positioned Panther could dominate a battlefield, destroying enemies before they even knew where the shots were coming from. The gun's recoil mechanism was a masterpiece of hydraulic engineering. When a gun fires, the recoil is immense. The Panther's recoil system used hydraulic cylinders filled with special oil that absorbed the recoil smoothly and in a controlled manner, allowing the turret to remain relatively stable even after firing. This meant the crew could relocate the target and fire again much more quickly. The Panther's optical sight deserves special mention. The Turmzilfernrohr TZF-12A was a high-quality telescopic sight with variable magnification and a sophisticated reticle that allowed for precise distance estimation. German optics of World War II were considered the best in the world, and the Panther's sight exemplified this excellence. On a battlefield where the first shot often determined the winner, the quality of this sight gave the Panther's gunners a decisive advantage. Now let's look at the heart of the machine, the engine. The Panther was powered by the Maybach HL2 30P30 engine, a 23-liter V12 gasoline engine that produced 700 horsepower. This engine was a work of art in mechanical engineering. 12 cylinders arranged in a V shape, machined with microscopic precision, working in perfect harmony to generate immense power. But there was a fundamental problem with this engine, a problem that would haunt the Panther throughout its existence. The engine was originally designed to produce 600 horsepower. It was increased to 700 horsepower to compensate for the Panther's increasing weight, which had grown from an initial design weight of 35 tons to 45 tons in production. This power increase without fundamental modifications to the basic design meant that the engine was constantly operating near its mechanical and thermal stress limits. The engine ran hot, very hot. The operating temperature was so high that there was a constant risk of fire. Early Panthers had a terrible problem with engine compartment fires. Engineers worked frantically to solve this, improving the cooling system and adding fire protection, but the problem was never completely eliminated. Many Panthers were lost not to enemy fire, but to mechanical fires. The transmission was another critical point of complexity and vulnerability. The The Panther used a 7-speed AK-7-200 transmission manufactured by ZF. This transmission had to handle the immense torque of the Maybach engine while controlling a 45-ton tank. It was an incredibly sophisticated piece of engineering, with precision helical gears, multiple clutch discs, and a differential steering system. The differential steering system deserves explanation. In a tank, you can't simply turn a steering wheel like in a car. To turn a tank, you need to make one track move faster than the other. The Panther used a system where the driver operated a lever that adjusted the power distribution between the two tracks. Turning left meant slowing down or stopping the left track while the right one continued moving, causing the tank to turn. This system was smooth and allowed for variable turning radii, but it was mechanically complex and prone to failure. The Panther's suspension was revolutionary. It used a torsion bar suspension system, where high-tension steel bars ran transversely through the tank's hull. Each road wheel was connected to a torsion bar that twisted when the wheel went up or down, absorbing the shock. This system offered an extremely smooth ride and was much more compact than conventional spring systems. The Panther had 8 road wheels on each side, arranged in overlapping and staggered pairs. This staggered wheel configuration distributed the tank's weight very evenly along the track, reducing ground pressure and improving mobility on soft terrain. The Panther's ground pressure was surprisingly low for a 45-ton tank, only about 0.88 kilograms per square centimeter, comparable to the much lighter T-34. But this staggered wheel design, while brilliant in theory, created significant practical problems. On the Eastern Front, where the Russian winter brought temperatures below 40 degrees below zero, mud and snow would get trapped between the overlapping wheels. Overnight, this would freeze into solid ice. By morning, crews would often find the wheels completely locked by ice. The only solution was to light fires under the tank to melt the ice, a process that took hours and left the tank vulnerable. Some Panther commanders ordered their drivers to move the tanks periodically during the night to prevent ice from forming. Maintaining the interleaved wheels was also notoriously difficult. If an inner wheel was damaged, the entire series of outer wheels had to be removed first. In field conditions, this could take a full day of hard work. In comparison, American Sherman tanks with their single wheels and vertical spring suspension could have a wheel replaced in less than an hour. The Panther's interior was a study in ergonomics and efficiency, but also in cramped quarters. The crew consisted of 5 men: the commander, the gunner, the loader, the driver, and the radio operator who also operated the hull machine gun. Each position was carefully designed to maximize crew efficiency. The commander stood in the turret, behind the gunner, his head projecting into a commander's cupola that offered 360-degree vision through periscopic sight blocks. This cupola was one of the Panther's most advanced features. While most tanks of the time forced the commander to choose between good visibility with the hatch open, exposing himself to enemy fire, or safety with limited vision, the Panther's cupola offered both. The commander could rotate the cupola independently of the turret, scanning the battlefield while remaining protected. The gunner sat to the left of the gun, looking through the TZF-12 a telescopic sight. He had controls for turret elevation and traverse, operated by a hydraulic system that allowed precise and smooth adjustments. The turret traverse was particularly impressive, capable of rotating the entire turret 360 degrees in approximately 1 minute, which was exceptionally fast for such a heavy tank. The loader was positioned on the right side of the gun, performing one of the most physically demanding tasks in the tank. The Panther's 75mm shells weighed approximately 6.8 kilograms each. In intense combat, the loader had to repeatedly lift these heavy shells from the stock, load them into the breech, and then close the bolt, all within a confined space, with the tank shaking and rocking, often under enemy fire. The Panther's rate of fire depended entirely on the loader's stamina and skill. A well-trained loader could maintain a rate of 5 to 6 rounds per minute. The driver sat in the front left of the hull, with the radio operator to his right. The driver had extremely limited visibility through a small periscope. Driving a Panther required considerable skill. The tank was heavy and responsive, but also unforgiving. A misjudgment while navigating difficult terrain could result in the tank becoming stuck or, worse, breaking the transmission or damaging the engine. The driver's controls included an accelerator, a brake, a gearshift lever, and steering levers. Operating these controls, especially the heavy steering levers, required considerable physical strength. After hours in combat, drivers were exhausted by the constant physical demands. Communication inside the tank was via an intercom system powered by the tank's battery. Without this system, communication would be nearly impossible. Inside a tank in combat, the noise is deafening. The roar of the engine, the bang of the firing cannon, the rattling of the tracks, and the metallic sound of enemy projectiles hitting the armor create a cacophony that renders normal speech completely inaudible. Communication with other tanks was via radio. Here, the Germans had a significant advantage over many of their adversaries. Each Panther was equipped with a FUG-5 radio, a high-quality radio set with a range of several kilometers. Crucially, all Panthers had radios, not just the command tanks. This allowed for sophisticated tactical coordination that was impossible for adversaries who relied on flag or visual signals. Now, let's discuss the monumental challenges of actually producing the Panther. Germany in 1943 was fighting a war on multiple fronts, its resources were stretched to the limit, and Allied bombing raids were increasingly destroying its industrial infrastructure. Producing a tank as complex as the Panther under these conditions was an impressive logistical feat. The Panther required approximately 150,000 man-hours of labor to produce. For context, an American Sherman tank required about 10,000 hours. The Panther had over 8,000 separate parts that needed to be manufactured, heat-treated, machined, and assembled. The precision required was extraordinary. The transmission gears, for example, needed to be machined to tolerances of hundredths of a millimeter. Production was spread across multiple factories throughout Germany. MAN in Nuremberg was the main producer, but Daimler-Benz in Berlin and Maskinenfabrik Niedersachsen-Hanover also produced Panthers. Components came from hundreds of subcontractors. The Maybach engine came from Friedrichshafen. The ZF transmission came from Stuttgart. The armor came from various steel mills across Germany. Coordinating this complex production network while dealing with bombings, raw material shortages, and a lack of skilled labor was a logistical nightmare. Production managers performed daily miracles just to keep the assembly lines running. When a subcontractor's factory was bombed, engineers had to quickly find alternative producers or redesign components to use different suppliers. Material shortages forced constant compromises. As the war continued, high-quality steel alloys with rare elements such as nickel, chromium, and molybdenum became increasingly scarce. Engineers had to rework armor alloys, generally resulting in lower-quality armor that was more brittle and prone to splintering. Later Panthers had noticeably inferior armor compared to early models. Labor was another critical challenge. Skilled workers were scarce, either recruited for military service or working in other priority war industries. Panther factories had to seek alternative sources of labor, including less skilled workers. The quality of the labor suffered correspondingly. Inspections found defective welds, poorly assembled components, and generally substandard quality control. Despite all these challenges, production steadily increased. In 1943, 1,768 Panthers were produced. In 1944, the peak of production, 3,740 Panthers left the assembly lines. In 1945, before the collapse of production, another 507 were produced. In total, approximately 6,000 Panthers were produced between 1943 and 1945. But producing the Panther was only half the challenge. Making it work on the battlefield was another matter entirely. The first Panthers were rushed into combat at the Battle of Kursk in July 1943. It was a disaster. Of the 200 Panthers sent to Kursk, only 43 were operational on the first day of the battle. The others had broken down during the march to the front or had mechanical problems that prevented them from participating. The problems were numerous and varied. Engines overheated and caught fire. Transmissions failed under the stress of combat. The fuel system leaked. The cooling systems were inadequate. The spare tires became clogged with mud. It was as if each system of the tank had its own unique problems. Maintenance crews worked day and night, but could barely keep up with the rate of breakdowns. The field commanders were furious. They had been promised a super tank that would dominate the battlefield, and instead they received machines that could barely drive onto the battlefield. Angry reports went back to Germany demanding immediate improvements. The engineers worked frantically, identifying and correcting problems. Gradually, through months of modifications and improvements, reliability improved. But the Panther never became truly reliable in the sense that Allied tanks were. A Sherman could run hundreds of kilometers with minimal maintenance. A Panther required constant maintenance. The expected lifespan of a Maybach engine was about 1,000 kilometers, after which it needed a complete overhaul or replacement. The transmission was even worse, frequently failing after only a few hundred kilometers of operation. This unreliability had profound tactical and strategic implications. Panthers frequently had to be left behind during retreats because they broke down or ran out of fuel. The Panther's fuel consumption was voracious, about 3 kilometers per liter on roads and half that in open terrain. With Germany increasingly desperate for fuel, this was a critical disadvantage. However, when the Panther was functional, it was formidable. Numerous combat accounts demonstrate the tank's lethal effectiveness. In June 1944, shortly after D-Day, a single Panther ambushed an American column near Lullory, France. In less than 2 minutes, the commander destroyed 9 Shermans, forcing the entire column to retreat. The Panther, well-positioned and using its superior range, engaged the Shermans from a distance where they could not effectively return fire. Similar incidents occurred across all fronts. In Normandy, the Ardennes, Italy, and the Eastern Front, well-commanded and positioned Panthers regularly destroyed multiple enemy tanks before being eliminated or forced to retreat. The Panther's kill-to-loss ratio was estimated at approximately 5-to-1, meaning that, on average, each Panther destroyed 5 enemy tanks before being destroyed itself. This effectiveness wasn't just about superior technical specifications, although those certainly helped. It was also about tactical doctrine and crew training. German panzer crews were extensively trained, often with months of preparation before seeing combat. They were taught to use terrain to their advantage, to engage from hull-down positions where only the turret was exposed, and to prioritize threatening targets. German doctrine emphasized the tank as a mobile gun platform rather than an assault weapon. Panthers were trained to engage from a distance, using their top gun and optics to destroy enemies before they could get close. This approach maximized the Panther's advantages while minimizing its weaknesses. But the reality of the war in 1944 and 1945 meant that these ideal tactics were increasingly difficult to execute. Allied air supremacy meant that Panthers operating during the day were vulnerable to air attacks. British Typhoons and American Thunderbolts, armed with rockets and bombs, were particularly effective against armor. The Panther's top armor, only 16 millimeters thick, did not offer adequate protection against air attack. Fuel shortages forced Panthers to operate increasingly in a static defensive role. Instead of mobile maneuvers that exploited their mobility, Panthers were often used as mobile bunkers, stationed in defensive positions. This negated many of their advantages and made them vulnerable to flanking and encirclement. The Allies also developed tactics specifically for dealing with Panthers. Knowing that the Panther was most vulnerable on its flanks and rear, where the armor was thinner, Sherman units were trained to work in teams. One Sherman would distract the Panther from the front while others maneuvered to get flank shots. The Allies also became adept at using terrain and smoke to close the distance to Panthers before engaging them. The development of improved anti-tank ammunition also helped. The American HVAP, high-velocity armor-piercing, projectile could penetrate the Panther's frontal armor at reasonable distances. The British 17-pounder gun, mounted on the Sherman Firefly, was even more effective. The armor-piercing 17-pounder projectile could penetrate the Panther's frontal armor at 1,000 meters. There were also specialized variants of the Panther that deserve mention. The Jagdpanther, a tank destroyer based on the Panther chassis, mounted the powerful 88mm Pak-43 cannon on a fixed superstructure. This vehicle was even more lethal than the standard Panther, capable of destroying any Allied tank at extreme distances. Approximately 400 Jagdpanthers were produced, and they developed a fearsome reputation. There were also attempts to create an armored recovery tank based on the Panther chassis, the Birch Panther, equipped with a winch and boom to recover damaged tanks. This variant highlights an often forgotten aspect of tank warfare: the importance of recovery and maintenance. A damaged tank that can be recovered and repaired is back in the fight. One left on the battlefield is lost forever. The Panther's complexity also meant that field repairs were often impossible. A destroyed transmission or a burning engine required specialized workshop facilities to repair. The Allies had extensive maintenance networks with abundant spare parts. Germany, under constant bombardment and with stretched supply lines, struggled to keep its armored units operational. There is a fascinating philosophical aspect to the Panther's engineering that deserves reflection. The Panther represents a quality over quantity approach. It was a tank superior individually to virtually anything the Allies fielded. But its complexity meant it was produced in relatively small numbers and required disproportionate resources to maintain. The Allies, particularly the Americans, adopted the opposite philosophy. The Sherman wasn't as good tank for tank as the Panther, but it was reliable, easy to maintain, easy to produce, and the Allies produced them in overwhelming numbers. Approximately 50,000 Shermans were produced during the war. This numerical superiority, combined with superior air supremacy and logistics, ultimately proved decisive. There is a debate among historians and military enthusiasts about which approach was better. Proponents of the German design point to technical superiority and an impressive kill-to-loss ratio. Proponents of the Allied design point to reliability, ease of production, and the simple fact that the Allies won the war. The truth probably lies somewhere in between. The Panther was an impressive machine, a triumph of engineering ambition. But it was produced by a nation that was losing the war, with dwindling resources and running out of time. In that context, the Panther's complexity and resource cost may have been luxuries Germany couldn't afford. There's also the issue of diminishing returns. The Panther was significantly better than the Panzer IV, but required twice as many resources to produce. It was slightly better than the initially planned Panzer V, but required 50% more resources. Each additional improvement in performance required disproportionate increases in complexity and cost. At a certain point, good enough is really good enough, especially when you can produce more of them. The Panther's legacy extended far beyond World War II. After the war, both the United States and the Soviet Union intensively studied captured German tanks, including Panthers. Many features of the Panther influenced post-war tank design. Sloping armor became standard. High-velocity, long-range guns became the norm. The emphasis on quality optical sights was universally adopted. The post-war French AMX-50 tank showed a clear influence from the Panther design. The British Centurion tank, which served for decades, incorporated lessons learned from studying the Panther. Even Soviet tank design, although following a different philosophy, integrated elements of the Panther design. There are controversies and misconceptions about the Panther that are worth addressing. A common myth is that the Panther was invincible frontally. This is not true. While the frontal armor was formidable, it was not impenetrable. The British 17-pounder gun could penetrate it. The Soviet 85mm gun, introduced on later T-34-85 tanks, could penetrate it at reasonable distances. The American 90mm gun on the Pershing tank could easily defeat it. There's also the myth that Panther commanders had unlimited vision due to the commander's cupola. The reality was more nuanced. While the cupola offered good vision in all directions, the vision blocks were small, and the field of view through each one was limited. In complex terrain with a lot of cover, blind spots were a constant problem. Effective commanders had to constantly scan their surroundings, and even then they could miss approaching enemy infantry or tanks skillfully using terrain. There was also the question of how much damage the Panther could actually absorb. The thick frontal armor led to a perception of invulnerability, but Panthers were regularly knocked out by hits on the sides, rear, or top. The side armor was only 40 to 50 millimeters thick, easily penetrated by standard anti-tank guns. The rear armor was even thinner. Once enemy infantry or tanks gained a flanking position, the Panther was in serious danger. The dangers faced by Panther crews were immense. When a Panther was penetrated, the results were often catastrophic. Ammunition stored inside the tank could detonate, instantly destroying the vehicle and killing the crew. Fuel could ignite, turning the tank's interior into an inferno. Even if the crew survived the initial impact, escaping a burning tank through narrow hatches while wearing bulky overalls and helmets was extremely difficult. Tank crew casualty rates were high on all sides during the war. For Panther crews, the risk was particularly acute due to the high profile of combat. Panthers frequently operated in situations where they were numerically outnumbered, relying on their technical superiority to even the odds. When things went wrong, they often went very wrong. But there are also remarkable survival stories. Panthers with multiple hits, extensive damage, but still operational, limping back to friendly lines. Crews that escaped from destroyed tanks, often wounded and burned, but alive. The robustness of the Panther's construction, despite its mechanical flaws, provided some degree of protection for its crews. Maintaining a Panther tank on the battlefield was a continuous and often frustrating challenge. Maintenance teams had to work in harsh conditions, frequently under fire, with limited tools and parts. Replacing an engine or transmission in the field required lifting the engine out of the engine compartment using specialized equipment. This work could take several days. Panther maintenance manuals were extensive, covering every system in meticulous detail. Maintenance crews had to understand hydraulics, mechanics, electrical systems, and metallurgy. A skilled Panther mechanic was a valuable asset, and their loss could be as damaging as the loss of a combat crew. The logistics of keeping Panthers operational was a monumental task. Each tank required hundreds of liters of fuel, lubricants, hydraulic fluid, and oil. Ammunition had to be constantly replenished. Spare parts, from trackers to transmission components, had to be transported forward. All of this logistics became exponentially more difficult as the war continued and German infrastructure crumbled under bombardment. There are aspects of the Panther's design that, in retrospect, seem perplexing. Why design interleaved wheels that were so prone to icing problems and so difficult to maintain? Why use an engine that consistently operated near its thermal limits? Why make the tank so complex that it required vast resources to produce? Part of the answer lies in the context of the time. Engineers were trying to create the best possible tank, and in many respects they succeeded. The interleaved wheels offered superior travel and weight distribution. The powerful engine gave the heavy tank excellent mobility. Complexity was the price of capability. But part of the answer also lies in the organizational culture and decision-making processes of the time. There was a tendency towards over-engineering, towards pursuing technical perfection even when good enough would have been sufficient. There was competition between manufacturers and between different branches of the armed forces that led to suboptimal decisions. And there was pressure from senior leadership that frequently demanded unrealistic specifications. The Tiger heavy tank and the Tiger II supertank exemplified this trend even more than the Panther. These were even more complex machines, even more difficult to produce, even more prone to breakdowns. They were formidable when they worked, but they were produced in such small numbers that they had limited strategic impact. In contrast, the Allies generally adopted a more pragmatic approach. Tanks didn't need to be perfect, they just had to be good enough and available in large numbers. This philosophy, combined with overwhelming industrial superiority, ultimately proved to be the winning approach. Still, it would be a mistake to dismiss the Panther as simply superengineering. It represented genuinely innovative engineering that advanced the state of the art in tank design. Many of its features became standard in subsequent tanks. The balance of protection, mobility, and firepower it achieved set a benchmark that influenced tank design for decades. The Panther also demonstrated the importance of proper testing and development. Early models, rushed into combat before they were ready, were reliability disasters. Later models, after extensive testing and modifications, were significantly better. This lesson, that complex weapon systems require adequate development time, remains relevant today. There are also lessons about logistics and maintainability. A weapon system, no matter how technically superior, is of little value if it cannot be maintained in the field or if it requires disproportionate resources to operate. Simplicity and reliability are virtues that should not be sacrificed in the pursuit of maximum capability. The quantity versus quality debate exemplified by the Panther continues in modern military procurement. Countries frequently face choices between smaller, more capable weapon systems versus larger numbers of less capable systems. The answer is rarely clear-cut and depends on many factors, including anticipated threats, industrial capacity, and military doctrine. For the men who designed, built, and fought in the Panther, it was more than just a machine. It was a product of its time, born of desperate need and technical ambition. For the engineers, it represented the pinnacle of their capabilities, a chance to create something truly exceptional. For the crews, it was their home and their protector on the battlefield, a machine that demanded skill and courage to operate effectively. Production and combat statistics tell only part of the story. Behind every Panther were factory workers toiling long shifts in harsh conditions, engineers solving endless technical problems, logistics commanders performing miracles to keep units supplied, maintenance crews working through the night on repairs, and crews going into battle knowing the odds were stacked against them. The Panther remains one of the most recognized and discussed tanks of World War II. Its distinctive silhouette with sloped armor and long gun is instantly identifiable. For military historians and tank enthusiasts, it continues to fascinate as an example of ambitious design, formidable capability, and ultimately, unfulfilled promise. What the Panther demonstrates is that engineering, however brilliant, cannot exist in a vacuum. It must be considered within the broader context of industrial capacity, available resources, logistics, and the overall strategic situation. The Panther was a magnificent tank, but it was fighting for a nation that had already lost the industrial war. If circumstances had been different, if Germany had the resources of the United States, if the Panther had been introduced earlier with adequate development, if reliability had been resolved, if, history does not deal in hypotheticals. The reality is that the Panther, for all its technical merits, was not enough to change the course of the war. But as a monument to human engineering, as an example of what can be achieved when brilliant engineers are given difficult challenges, the Panther remains impressive. Every system, from the sloped armor to the high-velocity cannon to the torsion bar suspension, represented careful thought and skillful execution. The fact that approximately 6,000 of these complex machines were produced under increasingly desperate circumstances is a testament to industrial capability and human determination. For those studying military engineering, Panther offers lasting lessons on the importance of balancing capability with practicality, on the dangers of over-engineering, on the critical need for reliability and maintainability, on how technical brilliance alone cannot overcome fundamental strategic disadvantages. The Panther also serves as a reminder that behind every machine are people. The people who designed them, built them, maintained them, and took them into battle. Their stories, their skills, their sacrifice, are an integral part of the machine's history. A tank doesn't fight alone. It's operated by crews who must work together under the most stressful conditions imaginable. Today, surviving Panthers can be found in museums around the world. These preserved examples offer a tangible glimpse into the remarkable engineering of this machine. Standing next to a Panther, seeing the sheer size of the machine, the complexity of its systems, the thickness of its armor, provides perspective that photos and descriptions cannot match. For the countries that faced Panthers in battle, the tank left lasting impressions. Allied soldiers who survived encounters with Panthers often spoke with reluctant respect for the machine. Veteran accounts tell of the intimidation of facing a Panther, the fear of its powerful cannon, the relief when a Panther was knocked out. The story of the Panther is ultimately a human story as much as a technical one. It's about people struggling to create something remarkable under difficult circumstances. It's about the triumph of engineering and the realities of war. It's about ambition and limitation, about success and failure, about the human pursuit of technical perfection and the reality that perfection is ephemeral. In these times in which we live, where technology advances at breakneck speed, where machines become ever more complex and capable, the lessons of Panther remain relevant. Complexity must serve a purpose. Capability must be balanced with reliability. Technical ambition must be tempered with practical reality. And above all, we must remember that machines, no matter how advanced, are tools created and operated by people. The Panther's legacy is not simply a chapter in military history. It is a case study in engineering, an example of ambitious design, a lesson in logistics and strategy, and a reminder of the human cost of war. The crews who operated these tanks, the engineers who designed them, the workers who built them, were all part of a monumental human endeavor, executed under some of the most difficult circumstances in human history. When we reflect on the incredible engineering behind the German Panther, we must acknowledge both its achievements and its limitations. It was a remarkable machine that pushed the boundaries of what was technically possible. But it also demonstrated that engineering, however brilliant, exists within broader contexts that limit what can be achieved. The story of the Panther teaches us about innovation and adaptation, about the challenges of translating brilliant design into practical reality, and about how even superior machines can be overcome by numbers, logistics, and collective will. It is a story that deserves to be told and studied, not only as military history, but as a fascinating chapter in the history of human engineering. May we learn from its lessons, appreciate its technical achievements, and remember the human context in which it was created and used. The Panther remains, decades after the last firing of its cannons, as a testament to humanity's capacity to create remarkable machines and a reminder of the realities that govern their use. May the Lord God grant us wisdom to apply such technical capabilities with discernment and for purposes that serve the greater good of humanity.